Have you ever wondered what truly limits the performance of a transistor in a switching application, or why a simple circuit can sometimes fail under stress? It often comes down to one critical factor you might overlook. Load current fundamentally dictates the design and performance requirements of transistor driver circuitry by determining the necessary base current, power dissipation, and switching speed. A higher load current demands more robust driver capabilities, impacting everything from the choice of transistor to the biasing resistors and protection mechanisms. The influence of load current stems directly from the transistor's operating principles, particularly in saturation. To properly switch a transistor into saturation, where it acts as an effective closed switch, the base current must be significantly high enough to handle the collector current. This is often described by the forced beta relationship, where the ratio of collector current to base current is less than the transistor's intrinsic current gain, ensuring saturation. As the load current increases, so too must the required base current, placing a greater demand on the driver circuit to supply this current. Beyond simply achieving saturation, higher load currents also lead to increased power dissipation within the transistor, mainly due to the voltage drop across the collector-emitter terminals and the collector current. This power loss generates heat, which can quickly exceed the transistor's thermal limits without proper heat sinking or a more efficient driver stage. Furthermore, managing larger currents affects switching speed, as greater charges must be moved in and out of the transistor junctions to transition between states. This directly impacts the rise and fall times, crucial parameters in high-frequency applications. When designing, you must accurately characterize your load to select the appropriate transistor and driver. Consider whether the load is resistive, inductive, or capacitive, as each type presents different challenges. For instance, inductive loads can produce damaging voltage spikes during turn-off, necessitating flyback diodes, while capacitive loads requiring a driver capable of sourcing and sinking larger peak currents to charge and discharge them quickly. Understanding these load characteristics allows for the precise calculation of base resistance, ensures adequate current supply, and determines the thermal management strategy. This rigorous approach helps prevent premature component failure and optimizes overall circuit efficiency and reliability. A key concept here is the safe operating area, or SOA. Every transistor has a specified SOA diagram which delineates the limits for collector current, collector emitter voltage, and power dissipation that the device can safely handle. Exceeding these boundaries, especially with high load currents, risks thermal runaway and permanent damage. Engineers often employ driver stages with current amplification, such as Darlington pairs or dedicated integrated circuit gate drivers, to effectively provide the necessary base current for large load currents while minimizing the driving source's demands. These advanced driving techniques are essential for robust high-power switching. Ultimately, recognizing how load current shapes the demands on your transistor driver circuitry enables you to build more resilient and performant systems. By understanding the interplay between load requirements, transistor physics, and driver capabilities, you gain the expertise to make informed component selections and design decisions, ensuring your circuits operate reliably and efficiently under all intended conditions.